Hello, my conquerees. I'm your conqueror, Luke, here with another episode, video part of this free online course of covering your, basic fundamental algorithms and data structures to help prepare you to crack that interview for, well, anything you want to do. So this particular video will be covering another data structure. This one in particular is called the hash map, or sometimes called a hash table. This data structure exists across all programming languages with different names, and actually has one already done in JavaScript. So as always, remember, this is a good theoretical, fundamental thing to know about common data structures and how they work, their pros and cons, etc., and not something you necessarily have to implement in an interview. Again, get in the comments below if you do get asked one of these questions in an interview and they ask you to implement it, because I'd be curious to see if anyone actually does that. That'd be a really lazy interview technique, but it is what it is. Again, we're going to talk more about conceptually what they are, how they're implemented already for us in JavaScript, and we probably, if you have any experience at all, especially any of my students coming out of our full stack bootcamp, you've already been using them and you just don't even know it yet. And I'll talk about the implementation that already exists as of ECMAScript 6 or ES6 JavaScript already has one available for us. But again, we're going to be implementing our own version of it with some simple code just so we understand how they work. And that should be it. And I think this is my laziest possible prompt for this particular comment that says just implement a hash map data structure, because I don't really care about, unlike in finishing out my video on the singly linked list, I think it was important to have insert, traverse, search, print, and delete methods, but this one's going to be much more simple as we're basically making the JavaScript object, which in itself is already a hash map data structure. Hash map data structures work off of key and value pairs, right? So a hash map is a data structure that takes a key and maps it to a value and then stores it somewhere. And that right there is what we already know as the JavaScript object. It is an abstraction away from a hash map. So it does have a hashing function underneath the surface that we just don't see. The JavaScript engine runs it for us, and it gives us an easy key value pair data structure to use. So like I said, you've already been using them, and now you know it. Now you have a name for it if someone tries to pop quiz you on that, huh? Got him! So it combines lookup, insert, and delete operations in a very efficient way. Hash maps are very good at doing that. Basically, your key, like person.name. .name is the key property of that object that finds a value for us. So you would take the string value, such as name, you would push it through some kind of function that generates a unique key that we can then map it to, right? So you just write name as a property on the object, but it has to be mapped to some kind of key. So that's the point of the hashing function. It takes whatever input you got and should hopefully generate a unique output that can be paired to that value, so you can find it and retrieve it very, very quickly. So this is typically something that performs some kind of math operation on it. We're going to be using a very simple one that does have some trouble, which we'll talk about pros and cons coming up here in a second. So the result of that hashing function is the index of the key value pair. And again, it has to be unique to make sure that you're storing all your data correctly, right? And you can retrieve it quickly, because you have a problem when they collide. Those are called, the problem is called collisions in hash maps, where if your hashing function's not that good and you have two different inputs that go through your hash function that generate the same output, you're going to have a problem, and there's different ways to deal with that problem, right? So, uses in hash maps are things like database indexing, caches, unique data representation, lookup in an unsorted array, and lookup in a sorted array using binary search. Those are your common uses of hash maps, right? So they're really good at fast access and retrieval, right? They have an O1, big O notation of O1 access and retrieval elements, because again, they are stored with unique keys that can be found very, very quickly. They're very good at inserting and deleting, right? They're also typically big O1 operations. Key types. So unlike objects, which we know typically have to be converted and created as strings in JavaScript objects, hash maps allow for any kind of data type or object to be used as a key. So you are very flexible on your key types. You're not just stuck with strings and numbers, for example. And it can be memory efficient, right? Because hash maps are generally efficient for memory. The size of the hash table can be adjusted to optimize memory. So you have to have what's called a bucket, which I'll describe here in a moment, that is a specified length, right, for storing our data. So they can be memory efficient. Like I said a moment ago, One of the cons of them is you can run into what are called collisions. That's when two keys produce the same hash value, meaning if I put in two keys as my input into my hashing function, I should theoretically get two different hash values for my table. However, in the event that my hashing function ain't so good over here, then what's going to happen is you're going to get two key inputs, generate the same key output, and you're like, oops, I got a problem. Then that's going to lead to some slower retrieval time as well as insertion time that we'd have to deal with, right? There's no order in hash maps, meaning they don't maintain any order of the elements, making it difficult to iterate over everything in a specific order. But right, finding something quickly is the good part. Yeah, so I mean, like I said, they're memory efficient with what's given to them, but they can take up large amounts of memory when having massive amounts of data, which if you're in a memory constrained environment may not be the great data structure for you. And like I said, for insanely large data sets, that's when you see the degradation of the hash map in terms of its performance. So, if you have a bunch of random stuff that's coming in with dynamic key names, it can be pretty large, but not like massive large, then hash maps are a great tool for you to use, right? So to think about, the way I think about hash maps is think of them like a library, because in the library, books are stored on shelves, and each book has a unique call number. If you're American, you're familiar with the Dewey Decimal System. Well, at least most of us were from like elementary school. I forgot how it works by these days. But each book has a unique call number that corresponds to a specific location on a shelf. Similarly, in a hash map, data elements are stored in an array, and each element has a unique key that corresponds to a specific index in the array. So you have a librarian who can quickly find a book. You just give them the call number. A hash map can quickly retrieve an element by using its key, just like a librarian can quickly retrieve a book given its call number, right? So in this analogy, y'all understand that books can be misplaced on different shelves or lost inside of a library. If you have people coming in and messing with it, they put books out of order, put books on different shelves, and that's like a hash collision in this analogy, right? And that's when it causes elements to be incorrectly stored or retrieved. So that's how I think about them, and hopefully that analogy helps clarify all the technical mumbo jumbo I've thrown your way. And using the library analogy, you can even see how the bigger and crazier the library gets, how a hash map also has some difficulty, right? Because trying to find a book amongst a gorillion books is going to be more and more difficult, right? And it also means that there's going to be more possibilities for collisions should that occur. For example, if I have a new fantasy book and my fantasy book section is completely full, I'm going to have to extend that section or know to just move it down to the next section and say, well, the first item of the next section is a fantasy book. So that's also one of the ways you handle collisions in this analogy. Right, so like I was saying, that the hash map structure already exists in JavaScript. They're just implemented using objects, or an abstraction of hash maps under the hood, and you get to use the simple objects, which use key value pairs to store and retrieve data, which is what we're doing here. It's a form of a hash map, right? And it's the simple, most common way to implement one. So if I was a prankster, jokester, goofs and gaffs kind of guy, which I definitely am, I would absolutely be, again, read the room. If your interviewer seems like they could use a chuckle, or you've had a good rapport and you have a good social kind of understanding of the situation here, I would totally, if they asked me to implement a hash map data structure in an interview, in a JavaScript interview, I'd be like, yeah, sure. And I'd write like const person equals curly braces, name colon Luke, string value Luke. I'd be like, hey, there you go. There's your hash map. Simplest way I can implement it would be the object. And I'd be like, ha, 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 ha. And again, like I said in my previous videos, if you can get a laugh, that's a really good thing in an interview. But like I said, the map, capital M map object was implemented in ECMAScript 6 and provides a more advanced implementation of the hash map with additional functionality such as maintaining the order of keys and supporting any data type as keys, because remember, JavaScript objects are only can use strings and numbers as their key values. So I mentioned a keyword called buckets before. In a hash map data structure, the bucket is the container that holds the key value pairs, right? Think of them as the shelves in your library. Buckets are used when hash collisions occur. So like this is one of the solutions to stop hash collisions. So meaning when you have a collision, the hash map will just go across it. Like if you have two books that have the same call number, the bucket will act like the shelf where you just go down the shelf until you find an empty spot. And on that key, you say, hey, this key is offset by 6 extra books till we found an empty spot. And that is how you can use buckets to avoid that collision problem I talked about, which will be just important to understand one of the ways to handle a collision, right? You memorize an offset and move that key down that offset and say, here's an empty part of the shelf, and I'm going to offset it by 6 books. That way I know where it is with that new unique key value pair I gave it, right? The new unique key I gave it. So, yeah, the number of buckets, because there's different ways of handling it. There's that traversal way where you just go down and find the next available space. There's one called chaining as well. That's kind of out of the scope of this particular discussion, but yeah, it's when you start implementing buckets to deal with collision problems is when you begin running into more performance issues as well, right? So smaller buckets can reduce memory usage, but may increase the likelihood of collisions. More buckets or larger buckets can reduce the number of collisions and improve performance, but again, it'll hog more memory. So without further ado, I wanted to give you all that crash course on how hash maps work so we can actually begin trying to implement one in its simplest form here in this video. Because again, I realized in the last video series of singly linked list data structures, I went way more into the weeds of code than I probably should have. And even by the end of that video, the second part of that video, I was saying that, maybe I'll have a TLDR that covers all these at a high level with some pictures and diagrams. I think I'm going to do that, even if, some random comes along that video and is like, what is this video for? The description will hopefully clarify that part out here. But for you, anyone that's been following along regularly through this series, again, I'm trying to prepare you for that interview process, and being able to understand some of these fundamentals is going to be a very good spot to be in, and don't worry about trying to memorize the nitty-gritty code part here. But let's visualize how this hash map file works, how this code is going to work here, right? So like I said, we're going to call it clash hash map. We could call it also like week map or our map or my map, whatever. It doesn't really matter here. We can't use capital M map because that is already implemented in ES6 JavaScript, so we got to make sure we're not colliding with keywords there. So like I had said, when we're going to make a new hash map class, we typically determine what the size of our bucket is going to be. So I'm going to say there's going to be a singular argument for our constructor called size that will be the size of our bucket, and I'm going to default to a size of 50. So remember in JS you can provide default values for arguments in functions. So we're going to do that right there, so we can always just instantiate a new instance of hash map and not have to worry about giving it a size every single time. So what we're going to do is say we're going to have a buckets property on the class that will be a new array from its constructed size. And this will give us an array of that size with nothing inside of it, right? Not like null, not undefined, just an array of X size with nothing in it. Okay, so we have that large empty shelf in our library analogy. And from here, we also need a way to track the size, if we have to use it elsewhere in our code, of our hash map. So we're also going to take that constructor argument and assign it to a class property in case we need to use it elsewhere in this class object. All right, that's it for the constructor. And now we need to talk about our hashing function. So our hash function, our hash method, should take a key value, and again, this is where it returns a hash value for us to look up. Now, there's going to be a billion better options that you can probably link into your HTML, or if you're in a node project, more likely, you can always npm install and required or import it, right? If you're required, or import it if you're in TS. But we're going to do a really simple hash function here. I'm going to return a value to use across my class object here, and it's going to take the key, converts it to a string. We're going to make sure it does that. We're going to get the length of that string, and we're simply going to modulus it by its own size, the size of our hash map, right? So this will be a very simple way of generating goofy little keys that clearly will have an issue, right? Because if I get two keys that have a similar length of characters, I could accidentally run into some issues where the hashing function returns a outputted hashed key that's the same one of the same input, which could be an issue. So again, not the best way to do it, but it's going to be a fun way to progress from here. It's a very simple thing that will clearly cause collisions, but it will be super fast, right? Anyway, so inserting data into a hash map. Typically, you will insert it via a key and value pair, where the key is hashed and then indexed with that value. So we're going to say set item will be the name of our method here. It will take the key we wish to hash and the value we wish to index and pair it to. So what we're going to do is we need to get what the index is going to be, which is the hashed value of our key. So I'll say let index equal this dot hash of our key, and hopefully that generates what we need it to do. Now that we have that, we need to say, hey, if this doesn't already exist in our bucket, go ahead and add it and assign that initial value. So our first check or test is insert it if it doesn't already exist. So we're going to say if this does not exist currently in the bucket. So if I generate a key and it doesn't exist inside of that bucket, that means we go ahead and are just going to assign it as the indexed value in that bucket. No, here's how we do it. My bad. Because it's going to be a subarray like that. That's how we're gonna handle this data here. Because again, it's got to be a key value pair, right? Almost forgot that bit there. So we have our bucket. We're going to get an index for that bucket, add that index to the bucket if it doesn't exist, assign it an empty array space because that's how we're going to store our key and value pair, right? So I will say inside of said buckets bucket, we're going to say this dot buckets at position index push our key and value pair within. So there you go. That's how we're going to store our key and value pair inside of our lovely little bucket here. So again, we have an array of a size that has nothing in it. I'm not talking like placeholder values like the letter X or empty strings or undefined or nulls. I got nothing. So I got to make sure I generate the data type and then push in my key value pair into it. So this replaces that empty memory allocated spot in the array we've made and pushes in a subarray that contains the key value pair at position index, which is why we're taking this approach to it. So that's how you set an item inside of a hash map. You take the key and hash it, which will be the index. You add the index to your bucket. Right, so this basically generates the call sign for our book in our library. It then creates or finds the empty shelf space for this new book we have created, and we prepare the shelf space at that index position. If it doesn't exist, we find the empty spot on the shelf, for example, and then we add our book with its call sign like sticker on its side to that spot on the shelf, which is what this function or this method in this class does. Now, to get an item from our library, from our hash map, we simply need to know what key we are looking for. Again, that key should be from our hashing function. Every time we have the same input, we should theoretically be getting the same output. So the first line of code will be the same, where I learned to type first. Where we're going to hash our key and hopefully get the same indexed value that we got from the last time we hashed it when we inserted said item. We're going to say if the key does not exist in our thing. That means we got a bad call sign on our book. We typoed the key, or it doesn't exist. So we should return maybe we can throw an error if we wanted to. Throw new error. This key does not exist in this hash map. Or we can return undefined, or we can just do like a, return null or something like that if that the key doesn't exist somewhere inside of our hash map when we're trying to retrieve a value. So we'll just return null saying, I don't know, homie, you deal with it. Something went wrong with your key right there. Now, if that happens to be okay, what we end up doing then is simply looping through our list of each one of our possible buckets in our bucket. So I'll say let bucket of this dot buckets index. Right? So we're looping through the buckets in our list of buckets at that index position. We're going to say if our bucket at index 0 matches our key value, then we're going to return the second item in the little bucket, which is an index of 1. So index of 1 corresponds to the value in our bucket that we're looping through in this dot buckets of index, right? So we're basically saying go to this spot in our hash map, look at the bucket index of 0 for the key to make sure it matches the key we're passing in, and if it does, return the value, which is the index position 1 of our little bucket right there. And that is all we need to do to implement the simplest form of a hash map, which again, I'm really not going to add like a bunch more methods that you may want, like a delete and search and things like that for this hash map like I did in the previous videos, because I did say that it's more important to understand these things at a fundamental level and some basic ideas behind the code, and not like extensively code one out unless you're really applying for some kind of high-level job. I don't know, that's making a library where you have to write all this stuff. But again, understanding how this works will give you more information how JavaScript Objects works, and eventually when I cover the map data structure that was introduced in ES6, you'll understand how this stuff is working under the hood. And with these names of set item, get item, you probably also know this is how local and session storage works beneath the hood, where you generate key value pairs to store information in the browser. So all this stuff does come around and kind of melds together over time with this knowledge we're getting here, right? This is helping to hopefully demystify how the object works in JavaScript. All right, so we're going to say my map is going to be a new instance of the hash map class, and it's going to default to our size of 50. We have two methods to actually work with called get item and set item. We're going to set an item, and again, we'll pretend these are like books with our keys, like our call book signs right here. We'll do count of Monte Cristo, one of my personal favorites. One of my personal favorite books right there as well, and both the movies are pretty cool too. I like them. We'll say the next call sign for the next book will be Don Quixote. Another fun read if y'all haven't read it before. Gonna go slay some dragons. And we'll do 03 will be The Great Gatsby. I'm like digging in like my memory of like what's some like great books I read throughout high school or my adult years, because now all I do is read JavaScript documentation. And we'll do like maybe War and Peace as one of our other books in our library here. So you can see our hash map is slowly building out our library. We are generating some unique call signs to our lovely little hash map here. And let's go ahead and console.log a test where we say console log my map.set.get item. And let's say someone comes in going, I would like to read Don Quixote, please. The librarian will be like, okay, that's call sign book 002. Let's go find it on our shelves. Survey says it retrieved Don Quixote, no problem. Let's say we have a typo or a misplaced book somewhere. We get undefined as our return value there, since it couldn't find that particular index. So again, our hashing function, we got undefined and not null because technically this ran down. Yeah, it got undefined because there's nothing there at this position, but that index is still the same length. So our hashing function is not a good one, which I said this is an issue you're going to have with retrieving things when you have poor hash functions, because this generates the same index key as something else, and that gave us a problem. So yeah, what does that do? Yeah, there's our null. So again, because my hash function isn't the best, we had an issue retrieving a value, and you can see where that was one of our cons that we haven't coded for. But again, in data structures that are better implemented than this have way better hashing functions than this simple math we are doing right here. So we saw an issue here retrieving data when we had a typo key of the same length. Probably not a great hashing function, is that lesson we've learned there. But if I add an extra 0, then we do get null, which is the expected return value I was looking for. And then I realized what I had just done because of how poor our hash function is. And yeah, that's really it to the simple implementation of a hash map. Remember, they are key values, right? And yeah, that about does it for this video. I hope y'all appreciated and enjoyed learning the basics of a very simple hash map, how it corresponds to the JavaScript object, its pros and cons, and a good analogy to remember it in case you're asked about it in an interview. So get cracking out there, librarians.